Kees Cook. It's spelled weird. I was named after my Dutch grandfather, and vowels are strange in Dutch. If you want to see these slides, you can download them there. I have it again at the end. So, hello neighbors, with apologies to Fred Rogers and Travis Goodspeed. I like this greeting just out of sort of the history of Fred Rogers and his kindness, and I think the generosity that exists in this industry, I think, was something that really happens a lot when you go look for it. In particular, Travis sent me a bag of USB face dancer boards back when I was looking at debugging, finding bugs in the Linux USB protocol handling, which was much appreciated, so very neighborly. So about me, professionally, I have been doing this a while. I was a sysadmin at the Open Source Development Lab, which ultimately became the Linux Foundation. So I like to tell people I was working at the Linux Foundation before Linus Torvalds, but it's not entirely true. Then I moved to work on the Ubuntu security team to try to beat user space security into some sensible space, and then joined Google to work on Chrome OS originally, and now I'm basically a full-time upstream Linux kernel security hardening lead. So there's a lot of people that helped me get this job done. I moved to Portland in 2002, so now I consider myself a native. I've been a free software hacker for as long as I can remember, and was lucky enough to be on a team that won the DEF CON CTF 2 years in a row. I thought it was initially a fluke in 2006, and then we worked really hard to prove that we could actually do it again. That was awesome. Oh, right, and of course, I'm speaking for myself, not for Google. So I got to show quotes from other people. I like to send a lot of security hardening patches to Linux kernel. Linus does not appreciate it. This is his quote. I did not, in fact, stop sending patches. But I don't want this to be all about me. This is a group effort. I want this to be about all of us. So here's a much better quote that I found through this fantastic book, which is very dense and very scary. This is how they tell me the world ends, which is about like the sort of the cyber weapons arms race over the years. It's pretty interesting. Anyway, the quote goes, "The most likely way for the world to be destroyed, most experts agree, is by accident. That's where we come in. We're computer professionals. We cause accidents." This is supposedly from Nathaniel Borstein, who drove the creation of the MIME standard, which I think is apt. So to that end, I've liked to think of practicing with accidents is really capture the flag in a lot of ways, playing with these things. And my thought process on CTF has been there's effectively 3 stages that you're working on, right? You got to figure out what the flaw is. You know, do that work, understand what's actually going on, really understand the system and how you can manipulate it. And then you have this choice of 2 other paths. You can weaponize that flaw and mount the attack. This is sort of like the red team area. Or there's, you know, hardening the binary, the source, or doing whatever you need to and defend against attacks, which is sort of the blue team area. I have a somewhat weird view of this, which is I understand how bullets work, so I can either work on machine guns or body armor. This is overly militaristic, but it's not exactly inappropriate considering software flaws are being exploited to target, you know, journalists and political activists and their families. So there's a little overlap here in the reality of the situation. I ended up going the body armor route, but I do appreciate all the folks that are going the other way. They keep my phone free. So one of the areas of the defensive work that I spent a lot of time with the kernel is looking at how we can protect the Linux kernel from user space, from attackers, whatever. And there wasn't really a central concerted effort to work on this area back in the day. And I picked away at bits and pieces for a while and then realized there's no way I am ever going to be able to do all of this myself. It's going to take me too long to learn all the different architectures that matter, learn compilers, there's just so much going on. So I tried to sort of start herding cats and get people involved and announce this Linux kernel self-protection project back in 2015. And the main goals that we had were to remove entire bug classes, because chipping away at individual bugs is just a total game of whack-a-mole, and it's hard to make progress. And when you look at the lifetime of bugs in the Linux kernel, I have whole presentations on this. Right now, it's about an average of 5.5 years between when something is introduced and to when it is fixed. So, and I'm speaking of high and critical. There's a giant long tail of medium and low vulnerabilities. So I like to point out to people that it's a 5.5-year window. So right now, for all of you using Linux-based systems, there's vulnerabilities in your system that many of us have not found yet. Some people might have. So trying to get rid of the bugs at the beginning is pretty important. And then since there are always going to be bugs, we need to look at how do we get rid of entire classes of exploits. How do we mitigate that? How do we make it not easy for attackers? So it's been 10 years roughly. Have things improved? I'm going to show us some vulnerability trends. But first, I'm going to quickly take a look at Linux kernel flaws and CVEs. This topic has come up a bit because the kernel became its own CVE naming authority in February, which is to say that now the kernel maintainers, or really the CNA team within the kernel, are doing CVE assignments. Whereas before it was sort of general purpose distros. When they tripped over something that they cared about, they'd assign a CVE. And now the kernel CNA will assign CVEs for everything that's being fixed that looks like it might have any kind of security relevance under any kind of threat model, which turns out to be a lot of CVEs. And I can sort of show this a bit. So if there is the universe of all flaws in Linux, the omniscient view, the objective truth that humans cannot grasp, within there's some group of publicly known flaws. That's great, and I'm speaking of flaws generally, bugs, not necessarily security flaws yet. And then of the publicly known flaws, we're going to fix some. And of course, because we cause accidents, there's a bunch that are accidentally fixed that we didn't even know were flaws at all. So that's this little bubble on the side. Now, a subset of that is security flaws. And it was around here, as I was making this Venn diagram, I started to lose my mind. So we have known but unfixed security flaws. We have yet to be found security flaws. And we have accidentally fixed security flaws in this grouping. And the old CVEs were off in this corner, overlapping so many areas, I need to zoom in. So we've got a range of false positives. So a CV gets assigned, but it's not actually anything that we can do anything about. So there's false positives that are in a variety of not a security flaw. Is it a fixed flaw? Is it accidentally fixed? Is it magic? And there's stuff that there's false positives that aren't even flaws at all. Like, oops, that wasn't assigned correctly. And then there are true positives in the unfixed realm. And then there's, accidentally fixed, also true positives. But it's kind of in this weird corner. It's not covering the reality of security flaws very well. There's a lot of stuff that isn't being identified in the kernel, in the security flaw space. It just isn't a mapping for CVEs. With the new kernel.org CNA, we have a much larger mapping, but it tends to focus on stuff that's been fixed, which is a change and is a little weird, but it does create fewer false positives, like fewer in ratio of false positives, and we get a lot more coverage, which I think is good, although it creates an absolute nightmare for people who are tracking CVEs so that they know that whatever software they have has no publicly known vulnerabilities in it. But this is a reminder to people in that mindset. Our goal is to fix security flaws, not CVEs. CVEs are just a tracking method. We have a better tracking method now. It's still flawed itself, of course. Everything will be. But we have a much, much better mapping to reality now, which is, I think, fantastic, except, of course, people who were only tracking CVEs now have to deal with the fact that, oops, they now actually have to track a much larger percentage of things, but those are the same flaws you were supposed to be fixing all along. Anyway, there's a whole other topic, but I wanted, the idea of these Venn diagrams popped in my head, and then I was compelled to create insane graphs. But my point is, I can't compare trends between the old style of CVE assignment and the new style of CVE assignment, so doing a trend analysis right now, ignoring the new CNA, I can look retrospectively through the CVEs to get a sense of where things are, because it's hard to get a true objective ability to analyze these trends, but the CVEs give us at least some signal to talk about it. And just a nice shout out to the Ubuntu CVE tracker. They make my life really easy because for CVEs, especially high and critical kernel CVEs, they actually track when the flaw was introduced as well as when it was fixed. And for doing lifetime analysis, that's really critical because traditionally CVEs just say, oh, it's fixed in here, have a nice day. You're kind of like, okay, but how long has it been there? What else do I need to cover? The new CVE CNA has introduction commits as well as the fixed commits, but they don't assign severity because there isn't a threat model that they work against. So the Ubuntu tracker, it's a general purpose distro. It's a general enough threat model that I'm happy with their severities under most cases. But anyway, on to my damn lies, I mean statistics. So looking at things that mention buffer overflows or overwrites in the CVEs from 2010 forward, I see this delightful linear line that's going down. So that's good. Something's working. Of course, when I saw this graph, I said to myself, but where do we cross 0? So I stretched it out, and oh my God, it hits 0 in 2038. We will have no more buffer overflows in 2038. So by my highly scientific and statistically robust and totally accurate prediction, we will have no buffer overflows right around the time the 32-bit time T Unix epic wraps. So, yeah. Which brings us to another class of vulnerabilities, integer overflows. So where are we on integer overflows? Oh, okay, it seems to be like it's improving as well. And okay, let's stretch this out to, where do we get to? 2031, oh good. Oh, we will have fixed the epic wraparound before it happens, which hopefully is actually true. Yeah, and there's finding these extensions of the prediction is just giggling to myself the whole time making these slides because it was so funny. Anyway, this is generally good news. We've been making progress. That's nice. The actual frequency of bugs is coming down in these areas. Like array indexing, array overflows, underflows has been kind of flat, and I don't like that. In 2020 was this bleeding tooth vulnerability. And this is an array in a larger structure that has a fixed size. I don't remember off the top of my head how many bytes this is, but HCI max AD length is a fixed size. The compiler knows that number. It knows that it's an array. It knows how big the array is. So obviously when you have a memcopy and you're going to copy data that came from who knows where into this completely fixed, well understood size thing, You should not do anything with validating length and just blow past the end of the array, keep on going, overwrite pointers later on in memory, and do insane things. So I was filled with rage, and I said, okay, this has got to stop. Memcopy can't just be take a pointer and write forever off of it. It actually needs to be object aware. It needs to say, hey, this thing is only this big. And it doesn't do this because C for 50 years has been treating memcopy just as an address, like that for the destination is just an address. There's just no concept of anything, and people will deserialize strings of bytes into many neighboring structures intentionally. So we started refactoring the kernel and redefining memcopy, and so if we take a zoom in on the array now, okay, we're making progress. It's not a great signal, but we've spent a lot of time on this, which I'll get into a little bit later. So the question is, now where's the low-hanging fruit? We've clearly been squishing bug frequencies out of these larger classes. Well, as it turns out, use after free has absolutely skyrocketed. And I like to look at where it starts to really come up, like 2016 and on. I'm like, oh, so where we started trying to actively get rid of bug classes in these other areas, people went, okay, the easier space is to look at use after free and dealing with temporal problems, not spatial problems. Okay, that kind of sucks. A question, of course, I had after seeing that graph is, oh my God, like that's a huge number. Why is it growing? Where are these coming from? So did an analysis of where all the fixes, like what files are getting touched in the kernel when fixing use after free bugs. And some big ones that stand out that I can sort of point to are netfilter code, the Android binder interprocess communication driver, and IOU ring. And there's been a ton of research and mitigation work on use after free that's not all upstream yet. So the Google kernel CTF vulnerability and patch reward program. So you can get money if you point out a vulnerability, and you can get more money if you send a patch, please. Netfilter has been just receiving a complete beating on here, which is really interesting. And IOU ring got such a beating earlier that Chrome OS started turning it off. Android is really tight on restricting it. It just was seen as way too young an API and is too prone for errors. And then Android binder is one of the first targets of a full driver to be completely rewritten in Rust for the kernel, to just get rid of lifetime problems, all the spatial and temporal problems that go away when you're actually using Rust for things. And so I want to talk about how we drove down other bug classes. There's a whole list of stuff that I just off the top of my head. We've been doing a lot of stuff for a long time, but a lot of refactoring, a lot of removing bad language usage, fixing how the kernel arranges its internal stuff. But I really want to call attention to some of the other work that's, we improved the compiler to do a thing, improved the compiler to do a thing, improved the compiler to do a thing. It's like, that's not actually about the kernel source, that's actually about C itself. So it's time for another quote. This is Yoda talking about the C language, which is, ambiguity is the path to the dark side, leads to confusion, confusion leads to flaws, flaws lead to suffering, and I sense much ambiguity in you, C. Yeah, C supports ambiguity, but we can fix that. So there's the whole class of undefined behavior, which is a really hilariously well-defined thing for compiler folks to talk about, and it is a source of a lot of flaws. But honestly, it is just a special case of language ambiguity. And of course, there's no memory safety, no lifetime enforcement, no safe concurrency in C either. But our choices here, as in the Linux kernel, are what do? We have to remove ambiguity in C and write new stuff in Rust. So what do I mean by ambiguity in the language? And I have 100 examples, but I'll talk about a couple ones that I think are pretty clear. So the first one is uninitialized stack variables. It's important to remember that there is no such thing as uninitialized. It's just whatever was there before. And as an attacker, if you can control what's going on, you can control what was there before, which means it's very, very well initialized. And yes, my garbage example here, the compiler will warn you in this case, like, hey, you didn't set on the stack before you used it. But it loses track of things very, very quickly. If you pass anything by reference, if you go through any unusual optimization paths, the compiler just sort of loses track of it and says, I don't know if it's initialized. Weirdly, the optimizer does, but that's okay. So this is an ambiguity. What is in this value? I don't know. It's sort of non-deterministic in the sense of the programmer's intent. But this was created. Trivial autovar init equals 0. You just say, everything's 0 by definition. And if you assign a different value later, an optimization pass will just get rid of the 0 assignment. You're all good. Everything goes away. The compiler will still warn when it can. And it becomes deterministic. And it's safer in almost all contexts. So if you've failed to initialize a thing, you've got a null pointer, which is usually handled. You've got a 0-length string, so nothing's overflowing. You've got 0 bytes to copy, and you've got UID 0. Okay, so not always perfectly safe, but it's much better than that. There was an enormous amount of pushback from the compiler community on this because they said people will depend on these variables being 0. It's like, yes, that's the point. And they did not want to fork the language. Again, I do. I would like a safe C. You can have your crazy C, but let's get something that actually works and is deterministic. It's not ambiguous about what's going to be there. So here's another one, array bounds checking, right? The thing that filled me with rage over Bleeding Tooth. So fixed size, we can in fact do bounds checking here. We have now repaired all of the complete insanity. It was just pick up a rock and there's another rock under it, just kept going with all the weird garbage in the compiler where it would sort of refuse to check array sizes for like a lot of bizarre ancient reasons, compatibility, all compatibility. But we've got this flexible array style, which is, well, we'll define it at runtime how big it is. And so C goes, well, I guess I don't know anything about the array, and it just gives up, which is, we don't want that. We would like to be able to say, if I have an array, I know how big it is. So we've added now the counted by attribute. So you can hint to the compiler, like, hey, yeah, it's sized at runtime, but here's where you go find how many elements are actually in this array. And now, theoretically, you can get bounds checking on fixed and dynamically sized arrays. Oh my God, it's a miracle. I don't know how we could have ever thought to do this, says C, the only language that hasn't been able to do this for I don't know how many decades. But this is kind of a big deal. There are a lot of other ambiguities. I could literally continue to talk for hours about this stuff. So the real target lately that we've been staring at is dealing with the language. So I think of the C standard as strict, slow-moving, and that it prioritizes compatibility over robustness. And they have their reasons for doing this, but for me, trying to be really practical about what's actually happening on running systems, I need things to actually be dependable and unambiguous. So if you ever find yourself so cursed as to need to do this kind of a thing, the key to making practical progress in GCC, Clang, and MSVC is to use the magic phrase, I would like to add this language extension. And then they go, oh, not to the standard, and they go away. And they're happy to let you blow things up. So then you coordinate between the compilers, and the C standard can catch up when they're ready, when someone wants to spend the time to do that. And I've been trying to nerd snipe people into talking to the standards committee and getting things happening, and it's coming along slowly. The zero initialization might be coming in the future at some point, which was finished years ago. So that's removing ambiguity. The big one, honestly, is just using a language that's actually going to start from a position of memory safety. So writing new stuff in Rust is is becoming a bigger and bigger thing in the kernel, and I think in the industry. I think it's notable that when governments notice your dumpster fire, it's time to switch languages. So there's a bunch of links here on things saying, do not use C++ and C for your new projects. The implication being that they will not buy your software anymore. That's sort of what's being said. On the kernel side, this was a huge political debate, trying to understand how do we open up the developer community to include Rust? How do we get the build working? How do we make everything run smoothly? And this has been going on for several years now for a bunch of really awesome folks that have just been plugging away at it slowly. There's a lot of stuff landing into upstream, a lot of the bindings, trying to get all that done and get maintainers on board. And in the meantime, while that's going on, entire drivers have been written in Rust. We've got 2 full graphics drivers now. There's file systems, block drivers, network drivers. So the thing I said recently to someone is, if the Linux kernel can start using Rust with its rather aggressive ecosystem and grumpy maintainers, I really think anyone can start doing it. We did it. Anyway, so those have been my struggles, shared struggles. There's a lot of other people involved in this work. How are you doing? If you're just getting started, please keep it up. If you're already writing in Rust, you're awesome. You're defending the cloud from evil, the job never ends. Keeping the AI from consuming the planet. I do not want to be turned into paper clips, thank you. Are you jailbreaking devices so I can fully use my hardware? Also, thank you, and also I apologize for removing bugs, because you do need the bugs to jailbreak. That's a dilemma. Doing other stuff in the industry, I completely love it. I don't know, all of our work can be a struggle, but it makes a difference. I think it can be really frustrating and demotivating at times, but in the end, we're making progress, even in weird spaces like the kernel. I don't care if this is cheesy, but I'm going to go back to Fred Rogers, and I think it's a great quote. It's, what you're planning and doing are things that can be a real help to you and your neighbor. I'm proud of you. This is good work. So thank you, and enjoy the rest of the day.